last thing that we have to know about to help us graph things is something called multiplicity. And what multiplicity refers to is sometimes when you find your x-intercepts, and they've started with x squared minus 2x plus 1, and if you factored that, that factors nicely to x minus 1 and x minus 1. So if you were finding your x-intercepts, you would find that you have one x-intercept, but when you factored it, it happened twice. So there's still only one x-intercept, but we will say that that x-intercept has a multiplicity of 2 because it happened twice. And if you had this equation and used synthetic division and everything and factored it completely, you'd find out, oh, this has x minus 1, x minus 1, x minus 1. It has the x-intercept of 1 happening 3 times, so we would say it has a multiplicity of 3. And something interesting happens at x-intercepts when they have multiplicities bigger than 1. So that's the first thing we're going to do, is we are going to write out some notes beside this, just in the column there. First thing we're going to write out is what happens if you have an even multiplicity. Which means an x-intercept happens an even number of times, which is easy to see when a factor has an exponent that is either 2, a 4, a 6, an 8. And what's going to happen when you have an even multiplicity is that your graph will bounce. I put bounce in quotations because I don't think that's an official math word. The graph will bounce at the x-intercept. And if you have an odd multiplicity, in other words, the x-intercept happens an odd number of times, two things will happen. For the most part, you will have either an odd number of 1 or 3, anything bigger than 1. And then a little bit different if it's 1 or bigger than 1. If it's just a 1, and that's what we've done all the way through so far, all the graphs we've done, like we look at the graph we just did, can you see that all of these x-intercepts happen once? Anytime an x-intercept happens once, your graph goes straight through that x-intercept. But if you have an odd multiplicity of 3, 5, 7, or 9, something bigger than 1, your graph we'll call it either bends, or sometimes people like to say flattens out. At the x-intercept. So your textbook has drawn the parabola with the x minus 1 twice. Do you see that when you had that multiplicity of 2 at the x-intercept, it's bouncing off the x-intercept because it happens to be right at the bottom of the parabola, right at the vertex. And an x minus 1 cubed graph, well, you know how to graph this from transformations. This is just your x cubed graph moved 1 to the right. But an x cubed graph, you notice how it bent? There was a bend at that on that graph, and the bend is so much, right? Technically, sometimes this actually isn't enough of a bend because they want that bend to actually flatten out. So sometimes what teachers say is they draw that x-intercept, draw a tiny little flat line, and then draw it so it's connecting to that flat line. Because in that moment, it actually flattens out perfectly, but just for a moment. So the bend is quite significant. The higher the exponent, the flatter the bend or the flatter the bounce. If I go to Desmos here just quickly for you guys. And we look at y equals x squared, right? That's a bounce. What happens if it's x to the 4? It's flatter. X to the 6, flatter. X to the 8, flatter. X to the 100, ooh, really flat. Okay? Same thing if it was an odd number. X to the 1, straight through. X to the 3, a bend. X to the 5, more bend. More bend. X to the 701, woo, really flat for a long time. Almost looks sharp here, but if you zoomed in, it would still be nicely curved. But that exponent of 701 would be a multiplicity of 701. It's really getting flat. So that's why we say that our graphs either bounce or flatten out. Only if it happens once, it'll just go straight through at that point. So this is the last piece of information that's going to help us graph things. And if we go to example 3. We're almost done this unit. That's crazy. Okay? Example 3. For these ones with multiplicity, usually they give them to you already factored. So life is even easier. Your end behavior is a little bit harder though. Because in order to know the end behavior, you have to sort of multiply it up. Not completely. You just have to be able to say, what's going to be the highest exponent? And if this is to the power of 4, and this is to the power of 1, can you see that you're going to have, if you multiply it all out, 5 x's in the end? Because x times x times x times x times x, and all 5 of those will give you an x to the 5. You also have to look at the leading coefficient, and can you see that they're all positive? You have a positive x here and a positive x there, and all multiplied out will give you a positive x to the 5 in the end. So your end behavior acts like the line with a positive slope. There's our end behavior. Your y-intercept is still easy, but you have to do a little bit more mental math. You plug in 0 for x, and here you would get 1 to the exponent of 4 times by negative 2. So a little bit more mental math if it's already factored, but not hard. Just have to be careful. You plug in the 0 and do your order of operations correctly. But the x-intercepts are way easier. Plug in 0 for y, and it's already factored. So this is going to save us a ton of time because we don't have to factor it. In fact, we know that negative 1 and 2 are the only x-intercepts. So negative 1, 0, and 2, 0. And just to add our new notes of what we just learned, this one has a multiplicity of 4 because the exponent is 4. It would happen 4 times. This one has a multiplicity of 1. So adding the multiplicity doesn't change our steps. We still need to know the end behavior, the y-intercepts, and the x-intercepts. But the multiplicity is going to change or tell us what's happening at those x-intercepts. So when I go to graph this, I'm going to label all of my x-intercepts and y-intercepts. So negative 1, 0, 2, 0, 0, negative 2. And I know my end behavior says it needs to start down here and end up here. I now have enough information to draw this, okay? But again, I'm going to go through some common mistakes. First common mistake is to not use the multiplicity. And you know that you're going to make this mistake. Well, this is like, oh, there we go. Just, that's close, but you notice that you added a new x-intercept. You're never allowed to add more x-intercepts. If the only way you can make something work is adding an x-intercept, then you know you've done something wrong. When you found your x-intercepts, those are the only ones. So in this graph, we have to use the multiplicity. The multiplicity of 4, that's going to tell us it needs to bounce. So when we go up to this x-intercept, it bounces off. Go through this point. The x-intercept of 2 has a multiplicity of 1. Multiplicity of 1 tells us it's just going to go straight through at that point. No bend, no bounce, just straight through. So this allows us to graph things perfectly. All of your x-intercepts, y-intercepts, again, you're not concerned about what the minimum is, what the maximum is, that's okay. You leave that for next year when you take calculus. But for right now, we've got the end behavior and all of our intercepts, we're going to be fine. So let's look at part B. Part B, the equation was g of x equals negative x plus 1 cubed and an x minus 3. So, we're going to need to figure out the end behavior. It's a little bit harder. But basically what is happening with the end behavior, okay, it's going to be a g of x equals, we would look at each of these factors. Can you see there's one x here? There would be 3 x's here, x cubed, plus you have a negative out in front. Putting those all together tells us we have a negative x to the 4 graph. What does that mean for our end behavior? It's even, acts like a parabola, negative leading coefficient. There's our end behavior. Y-intercept, again, a little bit trickier because it's factored, but not super hard. You plug in 0 for x, you have negative bracket. 0 plus 1 cubed, 0 minus 3. This will be negative 1 cubed will be 1 times a negative 3. Negative 1 times negative 3 is positive 3. Your y-intercept will be 0, 3. And your x-intercepts this would be 0 if x is negative 1. This one has a multiplicity of 3, which tells us we're going to have a bend there. And this one is x equals 3. Has a multiplicity of 1, which means it's going to go straight through at that point. So we have enough information to draw our graph. We can plot our points. We have x-intercepts at negative 1 and at 3, and a y-intercept at 3. The end behavior says it's going down here and down there. And at the multiplicity, at -1, you need a bend, or it needs to flatten out. So again, sometimes what's helpful is drawing a little flat line right there. And now join your points. It needs to go up to this, go through that flat line, this one straight through, and we have our graph. Okay, I'd lose points on this right now because I haven't labeled anything, so I need to make sure. Label those points, then I'm perfectly fine. Yes?
Do I have to write like the whole point out? Or is it okay if I mark like the
Either one. Yeah. So labeling the points is easy to do because what I like about labeling the points is you're sort of double checking that you put them in the right place. But it is enough, if you would just do one here and one there, that's enough. Because then every ticky mark is labeled to be one, and you can figure out where they are based on that. Sometimes on final exams, they give you a graph and label those ones, then you don't have to label anything because it was given to you. Questions for practice on this one are 9, 10, 11, 12.